number 6 is the question, what is log of 1 million? All right. So the question is how many, so 10 to what number is equal to 1 million? Remember the logarithm, the value of a logarithm is the exponent. And so you already know the answer to this, I think, okay? Because a million is 10 to the 6th, okay? So the answer is 6. Right? Maybe I should be very specific, okay? The answer is log of 1 million is equal to 6, okay? Now do not say the answer is 10 to the 6th because 10 to the 6th is 1 million. That 10 to the 6th is exactly what you have here. The logarithm, the common logarithm of 10 to the 6th is 6, okay? 6 as in half a dozen, not a million, right? So make sure you understand that the answer to a logarithmic expression value tends to be kind of small, okay? Because you're just writing down the exponent. And so that's the answer. Now, if you have to explain why, you can say since 10 to the 6th is 1 million. And that really is what you need to say. That's about the only thing you have to say. Because again, the logarithm is asking 10 to what number is this, okay? So it's almost like this question is almost redundant. It's asking 10 to what is 10 to the 6th? Did you get that? 10 to what is 10 to the 6th? And the answer is the 6th, because 10 to the 6th is 10 to the 6th. All right, number 7, if a musical note has a frequency of 200 cycle per second, the note 1 octave higher has 400 CPS. Remember, because it doubles, right? What's the frequency of the note 1 octave higher than that? And the answer is, of course, it's 800 CPS. It's doubled from 400, right? Now, sometimes many students would respond 600 because it looks like it just increased by 200. 200, 400, the next number should be 600, right? That is linear thinking, and it's a sort of a linear pitfall because our mind tends to think linearly and not exponentially, all right? So in these questions about compound interest or frequencies of sound, you have to start thinking exponentially. So every octave, the number doubles. And so the next the frequency of the sound 1 octave higher would be 800. And then 1 octave higher would be 1600, right? And so on. List the first 7 Fibonacci numbers. You always start with 1 and another 1, okay? And then you can get the rule started. Because the next number will be the sum of the 2 previous numbers. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21. Do I have 7 numbers yet? 1, 2, 3, 4, 5, 6, 7. Yeah, I have 1 too many. Okay, so this is all you need. You don't even need this one. Number 9, the golden ratio is approximately what number? And this one, you really just should know it's about 1.6. You don't have to know more digits than this. Technically, you know, if somebody asked me what the golden ratio is, I would write the precise expression, which is 1 plus the square root of 5 over 2. But the square root of 5 happens to be around this number, 2.236, blah, blah, blah. But again, none of these things is required for your purposes here. The golden ratio, think of this, is about 8/5 or 1.6. How is it related to the Fibonacci numbers? Okay, so for this thing, maybe it's easier to write your answer in words. I guess that's the only way to do that. I'm going to write that, type it in. The ratio of 2 consecutive Fibonacci numbers approach. Wait, okay. The subject of this sentence is the ratio, okay? And of 2 consecutive Fibonacci numbers is a prepositional phrase here. I'm talking grammar. So the corresponding correct form for this verb is 3rd person singular. The ratio of blah, blah, blah approaches the golden ratio. Okay, so the ratio of 2 consecutive Fibonacci numbers approaches the golden ratio as n increases, goes to infinity. Okay, so in other words, you know, if F4 divided by F3 is close to the Fibonacci number, I mean the golden ratio, but F101 divided by F100 would be even closer, and so on. All right, number 10, compare the energies or the level of energy released by Quake A, 3.0, Quake B, 6.0. Well, B is double A, right? No, if you say B has twice as much power as A, you probably will not get any credit. All right, so remember what you have to do. You have to say, it's basically, the first one is 10 to the 6. That's what the 6.0, the magnitude 6.0 means. And the magnitude of 3.0 means this. And the ratio, of course, is the quotient, right? It's the result of the division. So this is 10 to the 6 minus 3. Remember, you always have to subtract the magnitude numbers and raise 10 to that number. So this is 10 to the third, and so it means 1,000 times, okay? And so maybe I should go ahead and write my answer here. Let's see if I can write this in a sentence. Quake B is 1,000 times as great. What I mean by that is the energy released by Quake B is 1,000 times that of the energy released by Quake A. So Quake B is 1,000 times as great as Quake A. So that would be a correct answer. And then how about a 3.4? And oops, that's not what I meant to do. And a 3.0, same way. You do 3.4 minus 3.0 because when you divide 10 to the 3.4 by 10 to the 3, then you get 10 to the difference, which is 0.4. Okay. Now, what is 10 to the 0.4? This is something you have to do on your calculator. All right. So you do 10 and then caret or maybe x to the y, and then put 0.4, okay? You know it's going to be less than 10 because 10 to the first is 10. 10 to the 0th is 1, and so 10 to the 0.4 is somewhere between 1 and 10, and you, according to your calculator, will get 2.51. Okay, so you could also say similarly, and maybe I will write it down here in a complete English sentence. Quake C is 2.51 times as, I don't want to say more than, because more than is different from of, right? So you can say the energy released by Quake C is 2.51 times as great as the energy released by A. Or Quake C is 2.51 times as great as Quake A. And that would be appropriate. Okay. And so that is number 10. We will start a new segment for the problems starting in number 11.